In this video, we'll look at Gauss's law and dielectrics. When we discuss Gauss's law, we assume charges existed in a vacuum. So we'll modify that law in general if charges existed where a dielectric was present. So let's apply Gauss's law. Let's use our capacitor. We'll apply Gauss's law to a capacitor a parallel plate capacitor specifically that has a vacuum or air, which is very close to a dielectric constant of a vacuum. We'll use a rectangular Gaussian surface and we'll enclose all the charge on the positive plate. So we'll apply our Gauss's law, epsilon naught, closed integral of E dot dA. That's just going to be equal to EA, or E naught A, since that's the electric field here. We'll call it E naught for vacuum, E naught, or air, which we're considering a vacuum. The dot product yields a cosine of 0, since the electric field will be perpendicular to the surface of the conductor. We've enclosed the entire area. The electric field will additionally, we're assuming that it's uniform. We're neglecting those fringing effects of the electric field at the corners. So that's equal to our charge. That charge is whatever enclosed on our surface there. That's the charge on our capacitor. So we get that our electric field is Q divided by epsilon naught A, where Q over A, that's our sigma over epsilon naught. If we then look at putting a dielectric between the plates of the capacitor, the charge that we've enclosed now becomes not just the positive charge, free charge we call it on the capacitor, that free charge that's free to move in the conductor, but we also have this polarization that occurs inside the dielectric. So due to that polarization, we have this induced surface charge, negative charge at the positive plate surface. So our Gaussian surface will enclose both of those charges. So when we apply our Gauss's law, that Q enclosed becomes the Q, the free charge on the conductive plate, minus that induced charge. It's plus the induced charge. The induced charge just happens to be negative, so we get plus a negative Q prime here. So our electric field is that free charge Q minus Q prime divided by epsilon naught A. So what we want to do is be able to relate that to our dielectric constant. So to do that, we know that our electric field is weakened by that factor of kappa, the dielectric constant. So that's going to be our E naught, Q over epsilon naught A. So we know that's what our electric field should be. Relating that to our Q minus Q prime in Gauss's law, that makes our Q minus Q prime, the free charge minus the induced charge in the dielectric on the surface of the conductor. That's going to be equal to our free charge divided by our dielectric constant kappa. And we can derive that using Gauss's law as we did. So we can rewrite our Gauss's law using that our enclosed charge, our Q minus, or free charge minus that induced surface charge, is going to be the free charge divided by kappa. Rewriting Gauss's law in terms of its integral form, we can put kappa in the integral. Putting kappa in the integral may be necessary if it's not the same dielectric throughout the volume between the plates of the capacitor. For example, we could have two dielectrics like this, where this is kappa 1 and this is kappa 2, right? So we could take our capacitor and have a different electric field on the left side and the right side. Additionally, we could have a scenario where we have a dielectric, but it takes the entire width of the capacitor, but it doesn't take up the entire depth of the capacitor. So that's why it's important to put kappa inside the integral. And our epsilon naught, we can pull out of the integral. That's always a constant, but our epsilon naught goes to kappa. Epsilon naught, kappa may or may not be the same throughout our integral, just like the electric field may or may not be same throughout the integral. So let's look at an example where the dielectric does vary in the capacitor. In this problem, we have a capacitor that was built with no dielectric material between the plates, A potential difference was applied across the plates, perhaps with a battery, and then that device was removed, the battery or the potential difference was removed. So we have a charged capacitor with nowhere for the charge to move. So we have isolated charge sitting on the capacitor. And then we insert a dielectric. We insert a dielectric, but it only has a width of B, which is less than the width of our diameter, which has a width of D. We want to see what happens then to the potential difference across the plates. So we'll go through our analysis. We'll look specifically at some numbers where the area, we'll look at a parallel plate capacitor, the surface area of the plates is given, the distance between the plates is given, that initial voltage that was applied is given, as is the depth or the width, I guess the depth of the dielectric and its dielectric constant. So since the charge will not change, we'll find that charge first. We'll find what is that free charge that appears on the plates. So we can use our theory that the charge is equal to the capacitance times the voltage across the plates. We know the voltage, we don't know the capacitance, but we do know the geometry. So initially we'll look without the dielectric inserted, and we can solve for our capacitor, C naught. That's when we have our vacuum or free space or air, between the plates of the capacitor. So now we can find the free charge on the plates. We can find that free charge is equal to that capacitance times that initial voltage applied. So that's what was initially put onto the plates of the capacitor. That will be unchanged when the slab is inserted, since our initial voltage V naught has been removed. So now we can look at what happens to the electric field. Our electric field is going to vary. We'll have an electric field in our free space area, E naught, and we'll have a different electric field. It'll still point from positive to negative, but that will be through our dielectric. We'll call that E1, but we know that E1 is reduced because it has this induced charge separation, polarization within the capacitor. So that reduces this E naught. E naught will not travel directly through this dielectric. So we'll use our theory to find those electric fields. We'll use Gauss's law. So our Gauss's law are in the free space area. And we'll look at this free space area. It doesn't really matter whether we do free space, dielectric constants, free space. We don't know what this little distance is. So since electric field is linear, we can just look at the dielectric as though it's sitting next to the negative plate and our free space next to the positive plate. So we'll do our integral for free space around the positive plate, and our charge enclosed will just be Q naught. And in this case, our kappa is just going to be equal to 1, because our kappa is air. Air has a dielectric constant of air is equal to like 1.0005. So to 3 significant digits, it rounds to 1.000. We could, round that up to 1. We're not going to do that. We're going to say that's just equal to 1. And we can find our electric field in the free space area. Then we can find our electric field in the dielectric slab. In that dielectric slab, our kappa is equal to 2.61. And we have used our theory here that Q minus Q naught, that's equal to the Q naught over kappa, right? So that's equal to Q naught over kappa. So we can change our Gauss's law, and we can find our E1 is just our Q naught over kappa epsilon naught A, and we get our electric field E1 here. So that's our electric field in this space. We have our E1, we have our E naught, and if we compare E naught and E1, E naught significantly larger than E1. It's greater than a factor of 2. It's a factor of 2.61, our dielectric constant. So now what we want to do is find the potential difference between the plates after the slab is inserted. And we can do that with using our line integral of E dot ds. So we'll move in the same direction of the electric field, so it'll just become our EDS. But we have different electric fields throughout our integral from the positive plate to the negative plate. So we'll just break up that integral, and again we'll break it up into two segments. We're looking as though this dielectric is sitting right next to our negative plate. Since it's linear, it doesn't linear and uniform, it doesn't matter. So we have our E naught times a D minus B times our E1 times B, and we can find the electric potential. Our electric potential then becomes 52.3, which is less than our initial voltage that was applied. So what does that mean? We could look at the work. We did that in the last video. That means that inserting our slab did not require work to be done as an applied force. The electric force of the electric field helped pull this dielectric into place, and in doing so, we decreased our potential energy a little bit, so the slab heated up. Okay, that's it for this video.